Alright, so making carbon-carbon bonds in organic chemistry is very important. And we've seen in previous videos where we can take a terminal alkyne, like this one shown here, and it has an acidic proton off the terminal carbon with a pKa of about 25. And so if we use a strong enough base, we can deprotonate this, something like sodium hydride. Remember, this acts as a base. It comes in, grabs the proton, and we put a negative charge onto the carbon. And so this gives us a nucleophile. We then go to step 2. We throw in a carbon electrophile. This carbon is attached to a bromine, so it's partially positive and can be attacked by a nucleophile. And so we have a negatively charged carbon attacking a partially positively charged carbon to make a new carbon-carbon bond. And so this comes in, does SN2 reaction, and we get to our final product. And so our final product would look like this. Remember to count your carbons. We have 1, 2, 3 carbons here, plus 2 more, that's 5. And so we have 1, 2, 3, 4, 5. And so making carbon-carbon bonds is very important. We've already seen this type of reaction, and so let's look at some other ways to make carbon-carbon bonds. So we can take carbonyl compounds and deprotonate the alpha carbon to give an anion, which would serve as a nucleophile. It can then go attack partially positive carbons, like I just showed with the alkyne, to make new carbon-carbon bonds. What do we mean by alpha carbon? So we identify the carbonyl, and the carbon next to it is what we call the alpha carbon. And so in this aldehyde case, we have a hydrogen on one side, and so we only have one alpha carbon. In the case of a ketone, we go to the carbonyl, we look beside it, and we see that we have 2 alpha carbons, one on each side. And we'll talk about how we differentiate between those two and how different reaction conditions can play a role in which side you add to, especially if you have different substituents and therefore it's not symmetrical. And then in esters, we have a oxygen on this side, so no carbon, and so again, only one alpha carbon. And so remember that these protons, I'm just going to draw the ketone over here, for example. This proton on the alpha carbon has a pKa of about 20 or so, 20 to 24, and so they are somewhat acidic. If we use an appropriate base, we can deprotonate these to make an anion. So an appropriate base to deprotonate this, its conjugate acid needs to have a pKa above 25 or so. And so for this, we could use LDA, for example. And so I'm not going to draw out the lithium, but here's the diisopropylamine. It can come in and deprotonate this and give us an anion on our carbon. We draw out the products of this. We have this negatively charged carbon. Remember, this also has a resonance structure where we push this down and move this up. If we draw this out, that means these electrons are now a double bond right here, and then we now have pushed these electrons up onto the oxygen, making it have a negative charge. If there's an H on here, we call it an enol. Since there's a negative charge, we call this an enolate. And so enolates can act as nucleophiles and attack electrophiles. We draw our protonated base over here. Remember, this is simply an acid-base reaction. We're transferring this hydrogen from the carbonyl compound to this nitrogen. And so if we want to think about the equilibrium, we want to take a look at the pKa's. pKa on this side for this hydrogen is about 20. pKa of this hydrogen on this side is about 35. And so remember, the equilibrium lies towards the higher number. And so this reaction would proceed forward, giving us this enolate anion, which can act as a nucleophile. So keep in mind that we need some type of base to deprotonate the alpha carbon. If we simply mix the carbonyl compound, it is neutral. With a alkyl halide, no reaction is going to occur. And so we have to add a base in order to generate the enolate. So if instead we first treat our carbonyl compound with a base, such as LDA, like I just mentioned, or sodium amide, so NaNH2, or sodium hydride, these are all three of these are strong enough bases to deprotonate the alpha carbon, therefore making a nucleophile. We then throw in some type of electrophile, and we can add these to our alpha carbon to make a carbon-carbon bond. And so the final products of these, remember the aldehyde has a hydrogen on one side, and so we are only going to add our carbons to the other side. Notice I have 2 carbons here. We're adding 2 carbons, and so our final product would look like this, where we have 2 plus 2, 1, 2, 3, 4. We have all the right carbons. And then for the ketone down here, again, this one is symmetrical, so it doesn't matter which side it reacts on. And we'll talk about unsymmetrical ketones in a little bit. Sodium hydride is going to deprotonate it. We're going to add 2 carbons to one side. And so we would get a product that looks like this. Make sure you have all of your carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's go through the mechanism of this ketone shown down here. And so remember, the first thing we do is we pull off this proton from the alpha carbon. In this case, we're using sodium hydride. Sodium doesn't mean anything. Hydrogen comes in, deprotonates this, and gives us a carb anion. And so our intermediate looks like this shown here. Remember that this has a resonance structure where we can move this lone pair down and move this pi bond up onto the oxygen, making something that looks like this. And so remember that we call this an enolate. All right, so enolates can attack electrophiles. We throw in ethyl iodide in this case, and we get an SN2 reaction on the carbon. Notice that enolates do not react on the oxygen, but they react on the carbon. And so we make a new carbon-carbon bond. Once this has occurred, we then get to our product. So as I mentioned, what about if we do this reaction with unsymmetrical ketones? And so we'll talk about the regioselectivity. Remember that regioselectivity means the preference for one product to form over the other. And so essentially, are we going to add to one alpha carbon versus the other when we have different substitutions? So let's look at this molecule shown here. And so notice that is unsymmetrical ketone. This carbon right here, the alpha carbon, remember, because it's next to the carbonyl, has a methyl group coming off of it and only one other hydrogen. This alpha carbon right here has 2 hydrogens coming off of it and no methyl group. And so we have an unsymmetrical ketone, which side is going to react. In our first reaction up here, we would treat this with LDA at very low temperatures, typically minus 78 degrees Celsius. And this is going to generate a particular enolate, which we would call the kinetic enolate. And then we would get alkylation on one of these carbons with our alkyl bromide. In the case of LDA, we get addition to the less substituted side, and so our final product for this reaction would be shown here. Remember, this is the kinetic product because we generate the kinetic enolate, which I'll talk about what that means in just a second. And then if we switch the reaction conditions from LDA to potassium terbutoxide or sodium terbutoxide or some other type of terbutoxide salt, we throw that in with the alkyl bromide. Notice this does not have 2 steps. It's all in the same pot at the same time. Instead of generating the kinetic product, we would generate what's called the thermodynamic product. And so we've added our ethyl group to the more substituted carbon, and we call this the thermodynamic product. So what does kinetic and thermodynamic mean? So a kinetic enolate forms when the hydrogen that can be removed the fastest is the one that's picked off. So think about my previous example, the carbon that has 2 hydrogens and no methyl group. Hydrogens are small and exposed, and so those 2 hydrogens can be accessed much faster than the one that's covered up by the methyl group. Thermodynamic, and so this results in the kinetic enolate leads to the kinetic product. Thermodynamic enolate leads to the thermodynamic product, and so this is the hydrogen that can be removed to give the more stable enolate. Remember, enolates have a double bond between the carbon and then a negative charge on the oxygen, and so they look something like this. And just as we talked about with alkenes, if this can be more stable, that's usually better, and so that's why we call it the thermodynamic enolate. And so in the case of the previous example, if we generated the enolate on this side of the molecule, so it looks something like that, we see that this alkene has 1, 2, 3 carbon groups coming off of it, so it would be tri-substituted. And then if we had formed the enolate on the other side, so here we only have 1, 2 carbon groups coming off of it, so it'd be di-substituted, therefore being less stable. So as I mentioned earlier, LDA gives us the kinetic enolate and therefore the kinetic product. And so if we use a strong base where the conjugate acid has a pKa above 30 or so, we're going to generate a kinetic enolate. So using LDA, sodium hydride, sodium amide, it's going to give you the kinetic enolate. And then using something that's a little bit weaker base, so the conjugate acid has a pKa of about 16 or 17, like potassium terbutoxide, sodium hydroxide, then we generate the thermodynamic enolate. And let's take a look at why this is. So why do we have these two different outcomes depending on which base we use? The answer is because it's dictated by reversibility. So if we look at this example here, we take this cyclohexanone, we treat it with sodium hydride. We know that sodium hydride, sodium doesn't mean anything, so we just have hydride as a base. And we have the option of pulling off this hydrogen here, or the option of pulling off one of these hydrogens over here. Imagine the probability is higher for it pulling off one over here. And in addition, there's no steric hindrance from this methyl group for the hydride to access this point. And so this is going to happen the fastest. It is going to grab this proton right here and then move those electrons back onto our carbon to generate our enolate. And so if we just draw this first acid-base reaction, not worrying about the second step here, our outcome would be the generation of this carbanion. Remember, it has a resonance structure to the enolate, and then we make hydrogen gas. And so this reaction, first of all, is not reversible because hydrogen is a gas, and so it escapes out of solution. So as soon as this forms, it's gone. And then secondly, think about pKa. pKa of this hydrogen here is about 20 or so. And then the pKa of losing one of these hydrogens is about 35. And so we have a difference of 15 pKa units, which is very large. And so this is not reversible, therefore meaning we get the kinetic enolate leading to the kinetic product. So instead of treating this with sodium hydride, let's treat it with potassium terbutoxide. Potassium doesn't mean anything, so we get a terbutoxide anion that looks like this. And it has the option of deprotonating this hydrogen or deprotonating this hydrogen. Remember that actually in this reaction, everything is combined together, so we don't have two different steps. And so again, for the same reason as earlier, we have a more probability of pulling a hydrogen off of this side, 2 versus 1. And then there's less steric hindrance on this side because there's no methyl group. And so again, probability is we're going to grab one of these hydrogens. And so that would give us a enolate or a carbanion. And so if we draw that out, forget this top arrow right here, we would actually move these electrons onto the carbon. We get our carbanion, and then we have tert-butanol as our byproduct. What's the pKa of one of these hydrogens? It's about 20. What's the pKa of the hydrogen on tert-butanol? It's about 17. And so there's only 3 pKa units different here. And actually the hydrogen, the equilibrium is probably going to lie a little bit more on this side since the pKa is higher. And so this reaction is reversible. When we get to here, remember we can draw a resonance structure where we make our enolate. And so for this one in particular, we would get something that looks like this. And so this gives us a di-substituted alkene in our enolate, 2 carbons attached. And so it's not that stable. And since this is reversible, we're able to go back to this point, and eventually we deprotonate this carbon and we generate the more stable enolate. So remember, this reaction is reversible. It's going back and forth, back and forth, back and forth between reactants and products. And so eventually we get to the more stable enolate. So we grab this proton and move those electrons onto the carbon here. If we draw out what that gives us, we would get this carbanion shown here, plus tert-butanol, and then the resonance structure from this gives us the most stable enolate. And so we would get to something that looks like this, and this enolate has 1, 2, 3 carbons attached to the alkene portion, and so it's tri-substituted, more stable. And so if you have something that has a pKa similar to what you're deprotonating, you're going to generate the most stable enolate. So in conclusion, keep in mind that strong bases where the conjugate acid has a pKa above 30 or so, like LDA, sodium hydride, sodium amide, it's going to deprotonate the less substituted carbon to give you the kinetic enolate and the kinetic product. If you use something that is a weaker base and has a pKa, its conjugate acid has a pKa more similar to that of the protons on the alpha carbon of a ketone, you're going to deprotonate the more substituted carbon in this case, generating the thermodynamic enolate and therefore making the thermodynamic product. What do I mean by this? The more substituted carbon, remember, would be this one here, so more substituted. And then the less substituted carbon would be the one shown over here. And so you can obtain 2 different products depending on which base you use.